Hello everyone. Let's do more examples of applied optimization problems. The first example is one of my favorite for obvious reasons. Okay, so here we go. A can of Guinness beer must contain 440 centimeter cube of liquid. Assuming that the can is described geometrically as a cylinder, find the dimensions of the can which minimize its surface. So here, the quantity that we want to minimize is the total area of the surface of the can. So here we go. Poof! We want to minimize the surface of the can. That's the goal. So the question says we can assume the can is a basic cylinder. So let's draw a picture of a can here. Poof! So here's a can of Guinness, and I'm just drawing over that can of Guinness a basic cylinder. As soon as you're dealing with a cylinder, because we're going to be dealing with the area of the surface of that can, and also we have some information about the volume. The basic dimension of a cylinder is, of course, the radius of that cylinder. So here we go. Poof, let's use R for the radius of the can and also the height of the can. So let's use H for the height of that cylinder. Poof. So these are the two basic variables that you need in order to fully study geometrically a cylinder, radius and height. So let's construct a formula for the area of the can. So here we go. So area of the can. Well, this area for the can, there's really three parts of it. There's the top part, there's the base, and there's also the lateral side of the can. So the total area is, let's go with the base first. So the area of the base plus the area of the top plus the area of the side, or the label, let's say. So let's start using letters here to simplify. So the total area, I'm going to use big A. Area of the base is just a circle of radius r, so it's going to be pi r squared. The area of the top is also another circle of radius r, so it's pi r squared. Sometimes in these questions there's no top or no bottom, so you would have only one of them and not both. And then the area of the side, that's probably the trickier one. The side area here of a cylinder is actually a rectangle, where the base is the circumference of the circle, and then the height of that rectangle is just given by the height of the can. So the area of the side is 2 pi r h. Worst case, you just Google it. Okay. So this is the equation to minimize, but right now the problem with this equation is that there's two variables. We need r and h. So that's a big remark here. Poof, we have two variables involved here, r and h. So we need to find a way to get rid of one of the two variables. These two variables, of course, are strictly positive quantities. R cannot be zero. If R is zero, there is no can. If H is zero, there is no can. So this is going to help us define that interval later. So here, the radius or the height, both of them, they need to be strictly bigger than zero. But again, we need to get rid of one of them. The only thing that we haven't used so far that is given in the problem is the volume of that can, and that volume is fixed. We say that we need to build a can where this can must contain 440 centimeter cube of liquid. So we know that this volume is fixed. So here we go. Poof. The volume of this can here is fixed at 440 centimeter cubes. So that's one of the constraints here. We cannot just use any H and any R. It needs to be chosen such that the total volume is 440 centimeter cube. The volume of a cylinder is given by the formula V equal to pi r squared H. And we know this volume is fixed, and we know the volume that we want must be equal to 440 centimeter cube of liquid. So we know that 440 must be equal to pi r squared h. So we have another equation. This is one of the constraint equation because we're dealing with the fixed quantity here, 440. Now we're going to use this in order to replace one of the two variables in my formula that I want to minimize. When you look at A, you see that in that formula, there's 3 occurrences of R, and we have only one H. So it feels like it might be an easier job if we just have to replace H as an equation that will only depend on R. And also when you look at the volume formula, if you have to isolate R, you'll need to divide and do a square root. Meanwhile, if you have to isolate H, you just need to divide by pi r squared. So let's do that. So let's divide by pi r squared to construct this formula for H. So with that constraint equation, H is equal to 440 divided by pi r squared. And this will be my equation that I will use to get rid of H in the total area formula for the surface of the can. So if you go back to the area formula and you replace H by 440 over pi r squared, you're going to get a brand new equation for A, where A is only going to depend on R. So here we go, poof. Now the total area of the can, which I now call AR because A only depends on R, is pi r squared plus pi r squared, which I can simplify to 2 pi r squared plus 2 pi r times H. And you can see here H was replaced by 440 over pi r squared. So now that formula for the total area only depends on the quantity R. So therefore, now let's build the line for the pure optimization problem. So therefore, what do we have now as a conclusion? We know that the total area AR is 2 pi r squared plus 2 pi r times 440 over pi r squared. Here we can simplify a little bit. You can cancel and simplify the 2 pi's, and r over r squared. You can simplify the r at the numerator level with the r squared at the denominator level and get this brand new equation. Poof. AR is equal to 2 pi r squared plus 880 over R. And now you should also take the time to specify the interval of optimization. We know R needs to be bigger than 0. So here the variable R is going to be strictly between 0 to infinity. So now this is our pure optimization problem. And now the interval, sadly, is a open interval. So we'll need to set up 2 important limits later on to fully finish that pure optimization problem. But anyways, that line here, so very, very important line here. So now the question is just a pure optimization problem, okay? Because we have a function and we have an interval. Now we're back to 6.4, so a pure optimization problem. Now that we're back to a pure optimization problem, I'm just going to go over quickly the computations, but now there's really nothing new. This is just like 6.4. We have a pure optimization problem. The first thing you always do when you have a pure optimization problem is you compute the derivative of your function to find any critical point. So here we go. So here a prime of r, so derivative of r squared is 2r, so you get 4 pi r, 1 over r, so r to the power minus 1, when you compute its derivative, you get minus 1, r to the power minus 2, so this will simplify to minus 880 over r squared. This equation will only crash if r is 0, so we don't care. So if there's any interesting critical point, you will find them by setting our a prime equal to 0. So if you bring the second term, the minus 880 over r squared, to the right side, you're going to get 4 pi r is equal to 880 over r squared. If you cross multiply, so if you bring the r squared on the left by multiplication, and if you bring the 4 pi on the right by division, you're going to get r times r squared, which will simplify to r cubed. and 880 divided by 4 pi will be 220. So that's the 880 divided by 4 divided by pi. And then if you want the value of r, you just need to compute the cubic root. So you get that r is the cubic root of 220 divided by pi. And of course here, always take the time to compute this value numerically. So you get 4.12. And of course, 4.12 is a number between 0 to infinity. And meanwhile, because we're asking for both dimension, if you need h, because we know what h is 440 divided by pi r squared, you can compute that h, the corresponding h is 8.24. So those are the two dimensions that you find from the critical point of that function when r is 4.12. But we need to make sure that this is actually the global minimum. So remember, this is part of the optimization problem. Even if that 4.12 and 8.24 will be the answer that we're looking for, you need to justify why it's a global minimum. So here, just using a table of outputs, so we can conclude correctly that this will be the global minimum. Because my interval is open, I need a limit going to 0 plus, and I also need a limit going to infinity for the open endpoint, and I will also compute the output of the area at my critical point, 4.12. So here for the first limit, I'll let you do that as an exercise, but if you compute the limit as r goes to 0 of 2 pi r squared plus 880 over r, because we have a bad division by 0, if you sub in your 0 plus, make sure you understand that this limit goes to infinity. So this means that if you're using a can with a very small radius, you're going to get this very long straw-shaped can, very weird-looking can, but this can will have like a very large area, so it's not efficient to like build these long straws to contain 440 centimeters of liquid. What about the other extreme? When r goes to infinity, basically you're building a can with that looks like a disc. So for r going to infinity, so for the second limit here, this one is a bit easier. If you compute the limit as r goes to infinity by replacing all the r's by infinity, you will get infinity too. So if you're designing a can to have a very large radius, the height will be very small, but the total area will be huge. So of course, now back to our table. So the limit to 0 plus is infinity. The limit to infinity is infinity, very large quantity. So of course, when you're computing the output at 4.12 inside your area formula, double check that you get 320.25. This is obviously the minimum. So poof, the conclusion here is that the absolute minimum is reached when r is equal to 4.12 centimeter, and then the corresponding height is 8.24 centimeters. So those are the dimensions that you need in order to minimize the total area of that can. All right, this example made me thirsty, so let's cut this video here. So for that example, that's it. That's all. Bye-bye, and cheers.